Okay, okay, started. So we just talked about the figure 2.10, 2.11, and 2.12 in the textbook. Please, if you don't have the figure, please refer to your group page. I posted these figures there. Okay, so and these are for the different shape of the things and also for the circumferential things. Okay, so you can take a look if you have textbook. You can read the textbook about this. Okay, and for the efficiency, one thing I want to add is there's a magic number of efficiency. No, I'm sorry. The efficiency, I think that's about it. And then let me talk about the thing effectiveness. And then another criteria to judge if the thing is good or not. That's called thing effectiveness. Okay, let me turn on my screen. Okay, effectiveness as an equation. Okay, so for some reason they didn't put the effect, they didn't put the equation number for that equation, but I think it's important. So thing effectiveness. The definition is different. It's Q with thing divided by Q of obviously without thing. So you compare two different situations. So you can just compare, you can have two pipes or two whatever, two devices, and one put on the thing, one put without the thing. Okay, see how much heat transfer. So this is actually straightforward, right? So the equation is 10 ml over square root of HA over KP, okay? So again, if it's case 2, maybe just use LC, correct length for this, and you should be fine. And effectiveness. So do you still remember what the definition of the Q efficiency? So what's the difference here? This is comparing with thing and without thing, right? With thing and without thing. Okay, that's straightforward. Effectiveness. If with thing has more heat transfer than the without thing, wait, that's the effectiveness. Okay, we get more heat transfer. Okay, with the thing. That's good. Okay. Do you know what the definition for the efficiency? Still remember? Anybody?
Efficiency is actual heat transfer over heat transfer if entire fin was the base temperature.
That's right. That's right. Efficiency is the current heat transfer versus the ideal heat transfer with the thing. So both numerator and the denominator, both are with things. Okay, that's efficiency. So with thing, that would be ideal case, which is, you know, entire surface is base temperature. So that's the maximum heat transfer you can have for that particular thing. Okay, so that's efficiency. So your current heat transfer versus the maximum heat transfer. So that's efficiency. Effectiveness is just compare to without thing. Okay, so that's a conceptual difference. So obviously you want to try effectiveness too. Every time you're adding a thing, you want to see at least it's the effectiveness should be greater than 1, right? Should be greater than 1. If it's 1, there's no reason to adding stuff like this. Actually, you want to check the value is greater than 1.13. That's the magic number, 1.13. Okay, so you know, in industry, in practical application, you don't really want to adding a thing. You know, it's trouble to adding something like this. It costs money. Okay, and maybe also change the integrity of the system or whatever. You're adding something. It could cause problem. Okay, and it costs money. So you want the stuff you add it significantly increase the heat transfer. Okay, if its effectiveness is less than 1.13, which is only 13% of the increasing heat transfer, we don't want to do that. Usually, it's not worth it. Okay, you want to see the effectiveness about maybe 2. Okay, 1.9 something like that with bigger effectiveness. Then you know invest more money on the thing. It will worth it in the long run. Okay, so I guess that's the number probably you want to remember, okay, for the future reference. You know, in the real work, real life work, when you design some heat transfer device like this, effectiveness is what you want to check. The bigger the number is, the better. Okay, so if your effectiveness is like 0.8, forget about it. That's a terrible design. Okay, it's possible. Okay, I'm telling you, it's possible, because adding thing, you really alter the flow. You might decrease the flow significantly. Okay, you know, the flow is good for heat transfer, convection, right? You need a stronger flow. So you might even possible that you decrease the heat transfer for your design. So it's important to check those things. Okay, effectiveness is one thing. Okay. One more thing I want to talk about is the thermal resistance. Resistance for thing wall combination. Well, every time I talk about thermal resistance, you might in your heart might hate it. Oh, come on, thermal resistance again, something new. No, you should appreciate the thermal resistance. Every time you see something like thermal resistance, that means you're trying to make your calculation life easier. Okay, remember, thermal resistance is the whole thing. You can add them together. Right? Every component you have a thermal resistance, you can add them together. Then the delta T over thermal resistance is just your Q. Okay, your calculation will be much easier if you adopt the thermal resistance idea. Always follow that, right? So the thin wall combination. What about what is the thermal resistance? Okay, think about this. You have initial thermal resistance R for the wall, right? Before you adding thing, you have, of course, you have the thermal resistance. Okay, then adding the thin part, you have a conduction in there. There's a component, right? Thermal resistance. Then you have a convection going out of the thin surfaces, right? That's the thermal resistance. On the wall, the area that without the thing, you also have a convection going out. So that's also a thermal resistance. So how do you put them together? Okay, it's easy, not that difficult. Let's say this is a thin wall structure. Okay, like this. Okay, if you have a textbook, that's figure 2.13. Okay, so this is the wall. This is the thing, obviously. Okay, so you have several thermal resistance. Let's say the first one is RF. Okay, RF. So it's the convection heat transfer. It's from the convection heat transfer through the thin surfaces. Okay. So it will be 1 over eta, which is the efficiency, times AF times H. H is the surrounding. So this is the RF, right? Okay, the thin convection through the wall, through the thin wall. Okay. Is that right? You know that convection total rate is what? Efficiency times A, okay, times AF, right? AF is the surface of the thing, times H, convection heat transfer coefficient, and the theta 0, right? Base temperature minus the ambient temperature, right? So it is actually theta 0, delta T, right? Theta is the delta T. Yeah, be familiar with the idea of theta. Okay, you previously probably use temperature all the time, but in the writing, people always use theta. Okay, over RF, right? Okay, so RF is the first component. What else? You have R wall. Okay, R wall F. So only at the fin region here, you have a conduction heat transfer. Is that right? You have conduction heat transfer from the wall to the fin. So you have to consider that, right? Is that 1 over K length? Is that right? Is that the conduction heat transfer? Okay, so that's the conduction part. What else? You have R0, let's say. What is 0? 0 is actually this. So wall area between the things. Okay, so in this entire system, you also have the convection from those areas without the thing, right? So it will be 1 over HA0. Okay. And there will be another one, wall 0. That's for the conduction inside the wall. Okay.
Dr. Zhang,
Yes, yes.
for R naught, did you put 1 over H times AB, area of the base? Or is that AO?
AO. I'm
Okay.
sorry, there's no AB in the drawing, so it's AO, right? Okay. So let me double check one thing. Give me 1 second. Yeah, I think I have the typo here. This is the area. L delta X thermal resistance, L is in the numerator, okay, for the cross-sectional area of the thing, okay. So this is delta X over KAO, okay. So these are the two conductions, okay, and 2 convections. So you have 4 thermal resistance together for the thing and for the wall. Okay, so the combination, you have the start from beginning to the end. You have total heat transfer. Let me use the next page. The total heat transfer will be the.
Can you go back real quick, please?
Okay.
I wasn't finished done copying.
Okay. Yes. Okay. So there are 4 components. Yeah, since we look at this page. So how we arrange it? You see, you have a conduction going into the thing and the thing and going out. This is the series circuits, right? The 2 items, RF and RW, there should be a series configuration. Okay, but in the thing and the area without thing, hey, these 2 are parallel configurations. They're together, right? They're not going one to the other. It's parallel. One component is the thing, one component is the wall, right? So these 2 are parallel. So inside each items, inside the thing, you have 2 items, RWF and RF. They are series. Okay, these 2 things, and it's parallel with R naught and R wall naught. Okay. Do you see that? Do you see the picture? So it should be circuits is like this. This is the fin part. This is the wall part. What without fin part. Okay. So fin part, you have two thermal resistance. So adding together, it's a series. The wall part without fin also 2 adding together, the series. But then the whole thing is parallel. So how do you construct it? It's 1 over, right? Parallel. So the equation is on page 52, equation 2.49. So the total heat transfer will be temperature inside minus temperature infinite. This is the theta, right? It's multiply by, you have two terms in parallel, okay? Parallel is this. How to do parallel is this. This is the first one. This is the thing, they are in series, right? Is that what we did in the circuits? Okay. Then this is the wall without the thing. Okay, you have two resistance there. Okay. If you combine them together, then the equation become T n T inside minus T infinite. Okay, this Ti is inside. Okay, very, very inside the wall. And look a little bit messy on the equation, but that's what we have. If you rearrange it, you can just use this two. I think this form is okay. Okay, but I just want to present you whatever wrote in the textbook. Okay. Okay. Anyway, you remember there are four resistance. Okay. And there are two of them are series, two of them are parallel, and between the two, no, within the two are series, and between the two are parallel. Okay. But it look tedious, look messy for the equation, but it's just the equation. Just apply it. I think it should be fine. Okay. So you got the equation. So whatever thing problem you should be able to do. If you consider wall and the thing, it's not just thing. Okay. Previously the problem, example problem what we did, it's only for the thing. Okay. Now we are looking at the thing wall combination. Okay. Because in the practical cases, you always consider also the wall part without the thing, the area that has no thing on it, right? You also need to know heat transfer. So that will be your total heat transfer. Okay, you should be able to calculate the total heat transfer with thing and on this wall. So the purpose is, previously we'll talk about the thing effectiveness, right? How do you calculate the total thing with the thing? So this is the equation down here. You know, you have four components, right? You can calculate the total heat transfer on that surface with the thing and with the wall. Okay. So in the denominator of the effective equation is just without the thing. So it's just a single wall. Okay, that would be easy to calculate. But with the thing, the total heat transfer will be this equation. Okay, these two are the same. I said Q total. Okay, it's not just Q thing. Okay, please be careful. You need to sometimes depend on a different application. Sometimes we want to just calculate the thing heat transfer. For example, if you want to just calculate the efficiency, you just need the thing heat transfer. Is that right? Okay, you don't need this total heat transfer. But if you want to calculate the thing effectiveness, you need to know the total heat transfer. You with the thing and with the wall. Okay, so then you have to use this Q equation. Okay, that makes sense. It's very important. It's very practical. You see, this heat transfer subject, this thing subject, especially I like this one. I like the future one, like heat exchanger section. Okay, later part of the textbook. That's very practical. Okay, how do you design heat exchanger, right? This is how to design a thing, how to do the calculation. If you design a thing, the thing you want to calculate is efficiency and effectiveness. Okay, make sure you convince your client, your customer, or your boss that your thing is good. Okay, effectiveness. First of all, you have to make sure the effectiveness is greater than 1.13. Right. So you need to calculate the overall heat transfer with the thing and the wall combined total. Okay, so now you need to use this circuits idea, thermal resistance. Okay, a lot of components here. It's complicated. So with the thermal resistance idea, with the circuits, it's kind of like straightforward. Okay, that's the total heat transfer. When you add the thing, you will achieve. Okay, so then compared to without the thing, then you will have your effectiveness calculated. Then in the thing design, particularly on just a thing design, you want to calculate the efficiency of that thing too, right? Then you just use you calculate the heat transfer with the thing only, okay, comparing to the ideal heat transfer with the thing. So in that sense, you don't need to consider the wall, just the thing itself, the heat transfer. Okay, so several things you need to make sure you know that the difference, why we do that. Okay, is that clear conceptual wise? Is that good? Okay. I think we can example. I think the example here talk about the circumferential thing. Okay, let's do the example. Any question before I go to the example? Okay. Okay, example 2.10. Okay, 210 is just basically just try to use figure 2.11 and 2.12. I think it's 2.12. You need to know how to use that figure. Okay, I posted on the group meet group. Okay, so probably need that table, that figure in hand. Okay, problem says the aluminum thing 1.5 centimeter wide and 1 millimeter thick. Okay, was placed on a 2.5 centimeter diameter tube. Okay, so it's a circumferential thing. Okay, so circumferential, it's which one? It's the third one, the third figure in figure 2.10. Okay, please refer to the figure I sent to you, figure C in 2.10. So that's the thing we are looking at. The tube surface temperature is 170, okay? And the ambient fluid temperature is 25, okay? Celsius, both of them. Calculate the heat loss per thing for heat transfer coefficient H130, and assume K is 200 watt per Celsius. Okay, for aluminum, you have properties, okay? So how to do the calculation? So you need those. So the total convection heat transfer coefficient is, okay, is this, right? So I think it asks you to calculate the total heat loss. Is that what we asked to do? Compute the temperature distribution inside a distribution and have a diameter this. Compare, okay. Oh, no, I'm sorry. I'm looking at the wrong problem. Calculate the heat loss, yeah. So we start from the maximum heat loss equals, if the surface temperature is entire the temperature of the base, right? That's the maximum. So reality is this, right? Your actual heat transfer is efficiency times Q max. Is that right? So you need to find the efficiency for that from the figure 2.12, okay? But the total heat loss we can calculate easily. So it's pi r squared 2 pi combined, okay? Probably let me write it down first. Okay, you will see. Okay, so let's look at this equation. See if everybody understands this equation. Look at your group me figure of the circumferential thing. Okay, circumferential thing. I think it's a figure 2.12. Take a look. See if you understand this equation. First of all, pi r2c squared. What does that mean? It seems like an area, right? And the pi r1 squared. What does that mean? This is basically pi r 2c squared minus pi r 1 squared, right? From the beginning, from this term. I just want you to fully understand what are these. First of all, why there's a 2 in front of the pi? Anybody? Just work with me. If you work with me, you understand it and by the end of the class. So you don't have to spend much more time after class, right?
Is it something to do with the circumference or no?
Okay. This is a thing. I think pi r squared, basically it's an area, right? See, the 2 reminds you that actually you have 2 areas, okay? 2 areas. Look at the sketch in 212, figure 212, the sketch. So for the thing, the total heat transfer through the top surface and the bottom surface. There are 2 surfaces, right? Are you looking at the sketch? I'm looking at the sketch on my phone. Is that right? So this is the total area, total heat transfer area on the thing. Okay, that's why there's a 2. There's the top surface and the bottom surface of the thing, circumferential thing, right? Okay, is that right? Everybody, first of all, do you agree? We're trying to calculate the surface area on the top of the thing and the surface area in the bottom of the thing. We're adding them together. They are the same. That's why there's a 2 here, right? Is that right? It's so quiet.
Yeah, it makes sense.
Okay, so then the 2 surface area. So we calculate the 1 surface area first, then multiply by 2. So that the other combine the surface area. Okay. So the top surface area, how do we calculate? We do pi r2 squared minus pi r1 squared. Pi r2 squared is the entire surface area, entire area on top. If it's a circle, right? That's a circle. If the radius is r2, r2c means it's a corrected radius, which plus the r2c down there is plus the length of this LC. LC is L plus half T. Basically, that's what we try to use to eliminate the heat transfer in the tip. Okay, so we try to use case 3 basically. Doesn't matter. We can just treat it as the outer radius R2. Okay, so R2 is R1 plus LC. Yeah. So this is outer radius. So it's a larger. It's basically is large circle. Okay, so you are calculating the area of the ring here. That's your thing. If you want to have a top view, look at this is the pipe in the circle. Inner circle is the pipe. The outer circle is the thing, right? Is that right? Is that how we calculate the area of a ring? Pi r2 square minus pi r1 square. Okay. R2, we use R2C. Outside, you have a little bit thickness of the thing, so you plus the half of the thickness. So a little bit larger than R2. Okay, slightly larger than R2. Okay. Right? Everybody understand?
Yes.
Okay. So that's the area times convection heat transfer coefficient. T naught is the base temperature of the pipe. Okay, now that's called maximum heat transfer rate. So we assume the entire thing has a base temperature T0. So T0 minus TW, that's the entire total heat transfer through the thing surface, maximum, ideal case. Okay, so we don't need to worry about the temperature distribution on there. If we are given the efficiency, your life is much easier in calculating the whole things. Okay, you don't need to worry about the temperature change along the thing direction. Okay, you just calculate the total maximum heat transfer, then multiply by a efficiency, then you solve the problem. That's your actual heat transfer. Okay, but given the efficiency, see, and that's important, right? Okay, is that right? That's the logic behind it. So what is efficiency for that one? Okay, so you can find the efficiency, from the plot 2.12. So from that plot, probably you can get your efficiency around 0.02 or 0.82, I'm sorry, from figure 2.12. Okay, some approximation, interpolation you needed when you look at the plot like this. These are like the Moody diagram in the fluid mechanics. Okay, they have limited number of curves. Sometimes your value, if the value in between, then you probably need to interpolate. So you need to find a ratio. In order to do this, you need to find the ratio R2C divided by R1. Okay, so this problem, to solve this first part, you even need to know R2C. You need to find out R1. Okay, T0 and T1 are given. Okay, so find out those. R1 is given, right? Is that right?
0.025 centimeters.
Yeah, it is given.
Oh, no, that's diameter. I'm sorry. So it's 0.0125.
125, right? 0.2C, you have equation to calculate L1, no, R1 plus LC, okay? LC is what? LC is, look at even on the diagram, it said LC, right? LC is L plus 2T. Basically is equals to R1 plus L plus half T, all given, right? So turn out to be equals what? R2C is 2.8 centimeters, so it's 0.028 meter, right? These are all the meters. You got the ratio, then you can use the plot. Okay, by the way, the plot, you probably also need to calculate ML. In order to use the figure 2, you need to know the bottom axis, right? LC 2/3. Look at the what is the bottom axis? LC, right? 3/2 to the power H over K, AM of 3/2. AM is the profile area. Profile area is a rectangle. It's L times T, right? So in this case, it's 0.396. Okay. So what is R2C over R1? 2.24. Okay. Can you look into the plot 2.12? Okay, this is very practical. Okay, in engineering, when you do the work in industry, you're looking at the plots. Okay, see if you have to know how to read the plot. Can you find a 0.82 for me for the efficiency? Take a look. What do you find? Based on the value calculated, what is the efficiency? So your bottom axis ML is very small, right? 0.396. So it's in the beginning of the plots. Okay, which those lines are always identical, right? Less 0.4, about 0.4. Okay, so what is your R2C over R1? 2.24. 2.24 is about the second curve from the top. No, I'm sorry. Second curve from the top is what? Oh, it's 2. Yes, that second curve on top is 2. So you can just basically follow the second curve. Okay, when the second curve, when the bottom axis is 0.4, nearly 0.4, so I can find, yeah, it's definitely less than 0.85. So between 0.8 to 0.85, right? So 0.82 is probably a good guess for the efficiency. Okay, that's this example. Any questions? I think I like this kind of problem. You don't need to know use much of the theoretical equations. You look into the tables and figures, find out the coefficients. You know, in order to find out the coefficient using this figure 2.12, you probably need to calculate some of the detailed variables, right? So then you can calculate the whole thing. So total Q for this problem is 60.97 watt. Or the maximum, I didn't write down the value. The maximum is 74.35 watt, right? Yeah. And it's BTU, 253.7 BTU per hour. Okay. 60.97 watt is the final answer for this problem, equivalent to about 208 BTU per hour. Okay. Okay. This is an example for circumferential thing. Okay. I think it's 11:48. Any questions? I have 2 more minutes. Is that good? So we're almost finished the chapter 1. I have one topic left. It's called thermal contact resistance. Let's do it next time, doesn't matter, Monday. Okay, then we completely finish the chapter 2. Okay, which is a very important chapter. Okay, fundamental of heat transfer, basically. Okay. If you don't have other questions, let me remind you the project due Monday. Okay, the second project due Monday, and after that, please start working on the third project, which is the rest of the content.
Yes, sir. Quick question for the
Yeah.
project number 2. Are the the things that we can choose from to do it on? Are they listed on Moodle right now?
The thing you can do it. You're here, right, in the class. I said it many times, right? It's starting from 2.8. No, 2.9 to the end of the chapter 2. Okay. So the second project is from 2.1 to 2.8, right? That's the content. And the third project was the rest of the chapter 2. The grading, everything is exactly the same. Okay, the grading scale. For those I posted the grade, look at the comments area. I put in the grading for each categories. Okay, and let's show you how I grade your project. Okay. Is that good? Okay, so have a nice weekend. Happy Friday. See you next week.